So yes, Viorica Patraucean, that's my full name. I'm a research scientist in DeepMind, and just to say a few words about myself before going a bit into the research that I do. So I did my undergrad in Bucharest, in Romania, in computer engineering. Then through Erasmus program, I got to Toulouse, and where I did a master's and a PhD, mainly focusing on applied maths, but with focus on 2D image processing. And then I moved to Paris and Cambridge for a postdoc program where I did research on 3D shapes and videos. And since 2016, I've been a research scientist in DeepMind and organizer of EEML since since the beginning in 2017. So yeah, as you can see, I've been working for quite a while with the visual data in different dimensions. So starting with 2D images and then going to 3D shapes and videos. And I could say probably that I'm a bit obsessed with the idea of solving vision, whatever solving vision means for everyone. So for me, solving vision means building a computational model of the human visual system. And of course, there are lots of practical applications that emerge when we have such powerful models. You can think of robotics, virtual reality, autonomous navigation, helping the visually impaired, and many more. But for me, this field is also very fascinating because I think it also allows us to learn more about how our brain works. So today I will cover a few different aspects related to video processing. So I will first motivate a bit why looking at videos at all. Then I will go through, I will cover a few popular video models and then mention a few efficiency challenges in video processing. And then ways we can address those challenges. So by looking at the learning paradigms, for example, using multimodal learning or self-supervised learning, and then focusing on a topic that is a bit more exotic, let's say, less explored, where we look at depth parallel models. And I will talk about how we can do depth parallelism at inference time, at training time. And I will also mention a few aspects of biological plausibility of backpropagation. And I will conclude with a short summary and let's say my vision for vision. How do we solve vision in the long term? Okay, so let's get into it. So why should we care about video? So most of the successes in machine learning recently have come from image models. So you're probably familiar with ResNet 50s, and AlexNet was the very first the first image deep network. And more recently, we have the Vision Transformer, which are all very good at certain tasks on 2D images. And then if we have such powerful image models, the simplest video models that you can think of is nothing but an image model applied frame by frame on the consecutive frames of a video. So this is what I'm showing here on the left. So on the horizontal axis, we have the time or the consecutive frames of the video, and then on the vertical, we have the different layers of the network. And we pass each frame through the network, and we get predictions for each frame. And each frame is treated as an independent observation. So during training, one iteration could take in either isolated video frames, or it could take the entire sequence and average the predictions over time to obtain the prediction. Now, the downside of this kind of model is that it cannot integrate temporal information. So you cannot reason about motion features, for example. And in addition, you cannot exploit temporal redundancy to improve efficiency. And yeah, these are the kind of things that we will be looking at today. Now, with this kind of frame-by-frame video model, as I said, they work reasonably well. But for practical application, especially, they can pose important problems. Like, for example, you might notice here this kind of flickering effect. So you have some parts of the frame that are labeled correctly in one frame, but the next time step, the label changes. And visually, it might seem, oh, this is a nice output, but in practice, this might not be good enough. Like when you think of self-driving cars, if you have a pedestrian that appears in a frame and then disappears and then reappears and so on, this could be difficult to deal with. So whereas when you would have a full video model that takes into account the temporal aspect and imposes temporal consistency, that should alleviate this kind of issues. So just to maybe convince a bit why it's important to reason also about motion, like this is the advantage that we get from videos. I'd like to mention a study that was done on humans, on patients recovering from blindness, like later on in life. So at that moment in life, they were already able to communicate, to speak, to say what they were seeing. So these were people like at 10 years old or 20 years old, and they had surgeries for correcting their vision problems, and then in the recovery time they were shown different kind of images to test their visual abilities. So they were shown the kind of images that I'm showing here in this slide. So, for example, you just have some simple objects, and then they were asked how many objects do you think there are in different scenarios. Like you have separate objects, you have overlapping objects of different colors, and so on. And they were also shown like natural images, like you see here a cow, and they were asked again, how many objects are there? Do you recognize the object? And so on. So importantly, these people had experienced this kind of objects through their other senses. So they had touched in their life a cow. They had they knew what a triangle is from their knowledge. And when these are the kind of results that they obtain. So here in light blue, you can see the control group, so people who have normal vision. So for them, all these questions are very, very simple, and they do perfectly well on these tasks. And then we have different patients that were in recovery. So we can see that when the objects are separated here, they all answer correctly. There are 2 objects there. But as soon as we start having overlap between the objects, or we have different colors, or they are asked to reason about depth, then they start to struggle. So they cannot give the correct answer. The same for the natural image. When they are asked, they don't recognize the object, and moreover, when they're asked to say, okay, how many objects do you think there are, they're just tracing the contours of the object and saying that, yeah, there might be, I don't know, 4 or 5 different objects there. Now, another type of images that they were shown is when they had motion attached to the pattern that they were observing. So now they have again overlapping objects that I've shown before, that they were struggling when the objects overlap. But now these objects started to move. So they would have different motion patterns. They would move in different directions, or they had objects with background clutter. But again, the object would have some consistent motion. And then in all these situations, the patients actually really improved their prediction once the motion was there. So they were able to perceive the motion, and this proves that motion is really important when learning to see. It's really important to recognize objects and to disambiguate the visual scene. So yeah, this is maybe a long story to say why I think the videos are really, really important in learning good models for the visual for our visual world. So a second type of model it's still really based on image models, like 2D image models, and then we attach an RNN to it, an LSTM, your favorite recurrent model, and then this can integrate information over time, and then it can learn to reason about temporal features like motion. So let's say this is an improvement over the simple 2D image model that we would just apply frame by frame. The downside to this one is that it needs large memory for training with the backprop through time. A different model that is very successful in terms of memory is based on 3D convolutions. So basically here we consider the video as a volume. So we stack the frames of the video along the time dimension, and then we use 3D kernels and we convolve our video volume with that to obtain activation maps. Now, importantly, these 3D convolutions, they are not they're not causal, because the temporal receptive field of the convolution operator is symmetrical in the temporal dimension. So to compute the activation at time t, we also have to look into the future. This can be made causal using masked convolution, but yeah, there's some overhead in terms of computation. So they are accurate, but they are not ideal, let's say, from an efficiency perspective. And there are quite a few 3D convolutional models that were very successful. So I should say these are successful for offline processing of videos mainly. So and they use they're based on 3D ComNets, and they use temporal striding, and in some cases they also use rely on inflated 2D models. So you do transfer learning. You have these image models that were pre-trained on some, maybe an ImageNet or some other data set, and then you just replicate, you just tile those weights over time such that you can apply that in on a video. So this is I3D model, for example, which is inspired from Inception, extended to videos. Another nice model is this one, for example, a slow fast model from Facebook, which has some inspiration from the human visual system, where they have this kind of two-stream system, one that looks at the video at a low frame rate, one at a high frame rate, and then combines activations. So in the same way that it's useful to reason about images at different scales, like different spatial scales, this model extends that same idea in time. So you use different temporal resolutions and extract features like richer features that allow you to perform a task. More recent family of models is based on this on self-attention. So the vision transformer is it's now a very hot model, is a hot topic. So basically, this model challenges the existing convolutional approaches and the inductive biases that we were using related to translation invariance and locality. And this model is inspired from the language community and treats image patches as tokens or words, and then uses self-attention to learn dynamic weights that can put more emphasis on particular parts of the image that are more important for the given task. So in this model, every patch can attend to every other patch in the image from the very, even at the very shallow layers in the network. So locality is not used as much as it is in ComNet. Although, yeah, let's say like the very first step of patching the image is still equivalent to a conv layer with large kernels and stride equal to the kernel size. So based on this successful image model, there were a few papers that proposed video models based on the exact same design ideas using self-attention. So they've just, let's say, extended the tokenization to the temporal dimension. So several proposals for video models were published, but importantly, they all rely on pre-trained weights from the image model, so from VIT extended to video, because otherwise the training can be quite unstable. These are very heavy models. They're large models. They need a lot of training data. So starting with pre-trained weights from the image model really alleviates the learning difficulties. So here, for example, in this paper, the model here is Timesformer. They compare different ways of applying self-attention. So you can apply self-attention only within a frame and then aggregate over time simply, or you can actually do self-attention over within the frame and over the time sequence. So yeah, they've investigated the different dimensions, how to extend the self-attention to the time dimension, and they obtained very, very good results on different benchmarks in video processing. Now we've seen these models. They achieve good accuracy on certain tasks on videos. However, there are quite a few challenges related to training such models and running them as well. So first of all, going to supervised learning, the labels are of course expensive, and in the same time they can also be quite ambiguous sometimes. Like, how do you choose the granularity at which to label your data? What are the right classes to consider? Will this, because if you train on a number of classes, will this transfer well to some other task that you want to solve later on? If maybe there you have a different classes. So there are all these questions, and yeah, I think the part with the labels being expensive is a major issue. So here I've also summarized a bit different challenges when it comes to latency, throughput, and memory requirements, and also the notion if these models are causal or not, because all these aspects are very important when we talk about real-time applications like robotics, autonomous driving, VR. All these require real-time execution. So yeah, like in a glance, we can see that, as I mentioned, the frame-by-frame models, they don't have very good accuracy. Whereas as we go to temporal models, like 2D that are based on RNNs or 3D COMNETs or video transformers, the accuracy keeps improving. However, this reverses a bit when we talk about latency and throughput. Of course, latency and throughput are better for frame-by-frame models and RNNs, whereas the larger models, the 3D COMNETs and the video transformers, they are very heavy, so their latency is very high. And yeah, you have here also, like in terms of memory, again, the 3D COMNETs and video transformers have high memory requirements. In terms of memory at test time, which is also very important, of course, like this image-based models, they are more efficient. In terms of energy efficiency, I think they're all pretty bad. Like if you'd like to try making a comparison between a GPU and how the human brain works and how much energy the brain consumes, you will quickly see that a GPU that runs maybe just one object detector consumes about 10 times more energy than the human brain, whereas the human brain does so many tasks in parallel. And yet it consumes so little energy. So there's clearly a lot of things that we need to improve about our systems to achieve like good energy efficiency, which is so important for embedded systems, especially. And then when we talk about causal, of course, again, we have the frame-by-frame models and the RNN models being causal, whereas the 3D COMNETs and video transformers, they are not causal. So a problem with these models is that the latency and throughput, they're dependent on the depth of the model. So if we wanted to increase the depth to get more accurate predictions, then this would automatically increase the latency, which is a downside. And of course, for video transformers, because of the self-attention mechanism, they have quadratic complexity in all dimensions. So this is a huge limitation when we think of processing long video sequences, for example. Maybe I hope you can see this in your display to understand a bit why latency and throughput can be problematic for applications. So here on the left, I'm showing a video at normal frame rate, 25 frames per second, and on the right, I'm showing the same video at 5 frames per second, which would be kind of the frame rate at which our detectors can run now, like our models can run now. So I can tell you that on the right, you see the tennis ball in only 1 frame. So I don't think you can actually play tennis if you were to see the ball in only 1 or 2 frames. So of course there are many works to try to improve these the downsides of these models, and they focus either on improving the efficiency of the image models, like by doing model compression, distillation, proposing lighter convolutional modules, or having some sort of budget methods. And then there is also people focus also on improving the efficiency of temporal video models, like using multi-scale or combining, adjusting the 2D models to include temporal features and the reuse of features or variable update rates or others. And to address the part with the labels that I mentioned, labels being very expensive to obtain, in all these kind of works, you can also think of self-supervised methods to alleviate the labeling cost. So, and I will now focus a bit on this part, like how can we deal with bypassing the cost of obtaining labels for videos. So this is just a quick sketch of the learning landscape that you're probably familiar with. So we have the supervised learning, which is kind of the most mature field at the moment, and then we have the unsupervised domain, where we try to learn the structure in the data without human-provided labels. Then, of course, reinforcement learning, evolution, but I won't touch on those. And recently, a topic that has become more and more popular is self-supervised learning, which sits somewhere at the boundary between supervised learning and unsupervised learning. So basically, in self-supervised learning, we use large data sets, and for which we don't have labels provided by humans, but for which we can generate labels automatically. And then we define some proxy tasks using these automatically generated labels to learn a mapping from our inputs to this to this label space. And then we rely on transfer learning from to transfer features learned in this self-supervised regime to transfer to downstream tasks. So downstream tasks that we actually care about. So for example, you can think of tracking or segmentation in videos, or action recognition, or other tasks. So you can imagine that in this kind of tasks, for example, especially like on segmentation, it's very expensive to obtain such labels. So using any kind of pre-training to have good features to start with, and then you fine-tune on these downstream tasks is very important. So lucky enough, when dealing with videos, we have lots of options for designing proxy tasks that are needed in self-supervision. Because in videos, we have several modalities, and then we can have tasks within modality or across modalities. So as you can see here, in a video, we have the input visual frames, but then we also have audio, and we can also have the language, like a transcript of the video, which can be obtained automatically, or maybe we have it like captions from humans. And here are some examples of works that are done in this space. So starting from the left with tasks that are defined on images, going towards the right to tasks that are defined in videos and the different modalities that we have in videos. So we have many works at the intersection of video and language, or video and audio. So yeah. And in all these different works, the most common learning loss used is contrastive losses. And I will just give some details of a work that we've published recently with my colleagues in DeepMind that is called Brave. So here the main idea is to use two different views of a video and regress one representation from the other. And this is built on top of BIAL, so building your own latents, if you're familiar with that work. So BIAL is different from contrastive losses. So in contrastive losses, you generally use you use positive examples and negative examples, and then you have a model that learns to distinguish between positives and negatives. However, the problem with that is that you generally need to have you have to be very careful how you build these negative examples, because if they are too easy, then they don't provide enough learning signal. If they are too hard, maybe they're noisy, and then they still hinder learning. And in general, it requires training with very large batches. So you have to show your model a large number of negatives for every training iteration, and this can be very expensive. So in BIAL, they propose this alternative method where you actually just regress. You have a two-branch network, and you regress the representation of one from the other. And BIAL was proposed for images. And here in our work, we extended the BIAL to videos. So basically, we have two views extracted from a video, one narrow view, what we call narrow view, and one broad view. And the narrow view covers less field, in less temporal field or less spatial field, but has a higher resolution. Whereas the broad view covers a larger view of the video, but at a lower resolution. And then we force each branch to predict the representation of the other branch. And then for downstream tasks, we keep the representation of the narrow view for downstream tasks. So basically, the intuition is that the narrow view has to learn the context in which that kind of action or that video segment would have appeared. So and in the same time, it might also learn to ignore details that maybe are not important. So because it has to regress this broader view that has a lower resolution. And then as broad view, we can use different modalities from video. So we can use audio, but we can also use optical flow. We can also use different augmentations on the video stream. For example, we use the random convolutions, which is an extreme form of data augmentation. So yeah, in detail, these are the losses that we use to train. So basically, in each head tries to regress the representation of the other head, and we have these two loss terms. In each term, one branch is on one branch we stop the gradients, because otherwise the learning would collapse. So yeah, and this kind of approach leads to really good performance, so state-of-the-art results on video and audio data sets. Okay, so I've covered. I tried to cover a bit the space of self-supervised learning that helps us alleviate the problem of labels, of labeling the videos. Now I will switch focus towards problems related to latency and throughput in video processing. So, and for this, as I mentioned, I will talk about depth parallel models. So the works that I've mentioned earlier that try to improve efficiency of video models, importantly, they all use a sequential execution mode over depth. So you have the data goes layer by layer into through your network, and all the layers are blocked until all the layers finish the computation for that one frame. And basically, we're saying that is not needed. And one source of inspiration, let's say, is the human brain, where So this is a nice paper from the neuroscience community, asking the question, how come is the human brain so efficient? So as I mentioned earlier, the human brain consumes like 10 times less energy than one GPU, and still does so many tasks. And their answer is that the massive parallelism that is used in the brain is responsible for the high performance that we are observing. So kind of the same inspiration was used long ago already in general computer processors. Maybe you've learned, if you've done any computer engineering, you might have learned about pipelining instructions, where the idea is that you break a big instruction, you break it into smaller chunks, into smaller sub-instructions, and then you pipeline those instructions so that over time you can maximize the throughput, and you can efficiently use your hardware resources. So you assume that you have parallel hardware resources, and then you just, this is a way to make them work efficiently all in parallel. So I will dive a bit into how we can do depth parallelism at inference time and then at training time. And in both cases, the focus is to increase throughput, reduce latency, and then reduce the clock cycles as well, but I won't go much into that. And I'll just mention briefly at the end the biological plausibility aspects. So for at inference time, I'm showing here like a standard frame-by-frame model, and the horizontal axis denotes the computation time, and on the vertical we show the different layers of the network along depth. And we unroll this model over time to process the frames of a video, but we take into account that computation is actually not instantaneous. So every time a layer processes a frame, it also advances in time. And when the network finishes processing that one frame, it can only then start processing the next frame. And yeah, we're just using here some color scheme to illustrate which frame, which input frame generates some activations. So for example, blue activations come from the blue frame, and green activations from the green frame, and so on. And now this is a purely sequential operation mode. And all the modules of the network, they have to stay idle until all the other layers finish the computation. But we are saying that this is completely wasteful and unnecessary. So all these gray layers that you see here, they're just idle most of the time. So what we are proposing is to use a pipelining mechanism. So as soon as a layer finishes computation, it passes the activations to the next layer, and then it can immediately start processing the next frame. So no need to stay idle until the network finishes processing that frame. And by doing this, we are basically just rewiring this unrolled model, and this leads to a considerably increased throughput of the system. However, here the latency is still the same. The change in connectivity only improved the throughput part. So to actually deal with the latency part, we are changing the learning loss. So basically, we're forcing the network to make predictions before processing fully that frame. So basically, yeah, predicting the future. So of course now we have a low latency, and this and importantly, this becomes now is like a knob that we can turn. Like if we want faster models, then we can we decide how much we shift this the labels that we have here. But in the same time, by having lower latency, we are also making the task more difficult, because then the model has to predict more into the future. And yeah, we've showed that this can learn. So even if the task can becomes more difficult, this still works. And we've shown that we can apply this kind of mechanism to various existing image models like DenseNet or Inception. And yeah, and this is like in a sketch to see how the different GPU looks when we have parallel resources available. How does this look like? So on the top you see a sequential model where every GPU just waits for its turn to come to process a frame, whereas on the bottom in our setting we have the fully parallel execution mode where all the GPUs work all the time. So this is a much better use of hardware resources. And of course, as I said, the task now becomes more difficult and we lose some in accuracy, but we can recover a good amount, a good chunk of accuracy by doing distillation. So we consider that we have around a standard video model, and then we distill from that into the depth parallel model, and that really helps learning. So yeah, maybe just to mention that the results I've shown before, they're actually obtained in an unfair way for our model, because our model is real time by design, and we are comparing it with a standard model that has high latency and which is not real time. But that was kind of the best we knew how to do when we published the paper. But there was this other paper that was published last year in ECCV, which proposes a nice framework for evaluating real-time models. So this towards streaming perception, where they actually let's say they separate the execution of the model from the evaluation. So you have this asynchronous evaluation where the model just writes whenever it finishes the execution, it just writes in a buffer. And then you have your evaluator job that just reads at regular time intervals. It just reads whatever it finds in that output buffer and evaluates against that. And in this way, you can actually, you do a fair evaluation. And they've shown actually that for models that have an offline precision of 38, which is decent, actually this drops a lot, like to 20, when you consider this fair, which is more correct evaluation mode. So I will just briefly go through how we can do training with the same kind of design principles, like to still have depth parallelism during training. And just going back to the original figure where I was showing how all the layers are blocked during execution, the exact same thing actually happens during training. So the layers are waiting for the forward pass to finish, and then they're also waiting for the backward pass to finish. Like you compute activations, and then you compute the gradients, and every layer has to wait until their turn to update its weights and so on. And again, this is we are arguing that this is unnecessary. So concurrently, colleagues from Google have observed that we can use pipelining mechanisms for training for image models, and basically they use pipelining for computations of activations and of gradients. But they require a buffer, like a large buffer, where you keep around activations for when you will need them to compute your gradients. And this is what creates this bubble here. So that is like a time where you need to stop, a time when you accumulate forward activations that you would reuse later on when you want to compute your gradients and to update your weights correctly. And we kind of take this idea to the extreme and say that actually for videos, probably we don't need to block. We don't need that kind of buffer. We don't need that bubble area. Because in videos, consecutive frames, they are very, very similar. So the question is, do we need to buffer? Like if we know that the activations of the next frame, they will be very similar to the activations of the current frame. Do I need to keep the activations of the current frame, or could I just overwrite with activations from the next frame and move on? Like to send everything, all the information, to send it forward in time. And this is exactly what we have proposed in our sideways work. So basically, here I'm showing sideways versus regular backprop. So at the top, this is exactly what we are doing. Like we are computing activations, and then when it comes to compute gradients, we take activations from later frames, so that we don't need to store activations in a buffer. So we just overwrite activations with the more recent activations and compute approximate gradients. And we've shown that this actually works very well. So like to have an image of what we are actually doing, like if we are to plot like this kind of landscape where we have on the x-axis the correctness of gradients, and then on the y-axis the speed of computing those gradients. So we could start at the very right with the Newton methods that have more correct gradients, and then going to the left to gradient descent and the stochastic gradient descent, we start getting more noisier gradients, but which are computed in a more efficient way. And our method would be there at the top with, let's say, even less, more biased gradients, but computed much faster. And actually, surprisingly, we've seen that with our training mechanism, we for smaller data sets at least, we obtain even better accuracy than the standard backprop. And the reason for this is that the noisy gradients, they act as a regularization mechanism in training. Now, sideways, as I've shown, it is a 2D model, so it's an image model. But at the very beginning, I tried to convince you that it's important to reason about temporal features, because motion is so important. So that's why we created this extension of sideways to try to take into account temporal features. And this is our recent work, Skip Sideways, which was presented just 2 months ago, or in CVPR. So basically, we are repurposing the role of skip connections to be able to extract temporal features, even though we are like in a 2D model framework. So as you already know, probably skip connections are used to create shortcuts over data paths to avoid vanishing gradients, and they were proposed like in ResNet in residual networks. In our pipeline setting, we showed that skip connections can be used to create shortcuts over time. And this is what makes our model temporal and gives it the possibility to reason about temporal features. So if for people who are familiar with the temporal shift modules paper, for example, there we have a very similar, they have a very similar setting where you have a 2D model, 2D image model, but you want to have a temporal, the ability to extract temporal features. So basically there they shift manually activations at different time steps so that they can combine, so different layers can combine activations that originate in different frames. And yeah, as I said, they have to do this like manually to do this shift. Whereas for us in our setting on the left that you see here, because we have this this pipelining of operations, and we always send all the information forward in time. When we add the skip connections, this combination of features that originate in frames from different time steps, this occurs naturally. So yeah, we don't need to do this by hand. And importantly, it doesn't require any additional buffering. So, and these are the results that we've obtained on different popular video benchmarks with our skip sideways and compared with our sideways, our previous sideways. So we can observe that the accuracy improved significantly on all the benchmarks, and especially like the kinetics benchmark, which is a large scale benchmark. And to our knowledge, this is the first work to show approximate backpropagation schemes working at large scale. So, like just a brief comparison between the models that I've shown. So we have backpropagation, GPipe work that I've mentioned from Google, and then sideways or skip sideways from our team. We could say that backprop and GPipe, they're more general in the types of inputs that they can process. So they make no assumption about the inputs. Whereas for us, for sideways and skip sideways, it is very important to deal with temporally smooth sequences, and we're saying that videos are exactly that. So we should exploit that smoothness in time that we have in videos. And then, backpropagation based on chain rule, and GPipe and ours are similar in that they both use pipelining of operations. Backpropagations require blocking of operations, whereas GPipe has a partial blocking, and ours doesn't require any kind of blocking of operations. So, as I mentioned, as soon as a layer finishes processing a frame, it sends the activations to the next layer and can start processing a new frame immediately. Our model doesn't require buffering, whereas the others do require buffering. And our method, because it bypasses buffering, this results in using approximate gradients, whereas GPipe and backprop, they use more correct gradients. So maybe just to say very few words about the biological plausibility or better say implausibility of backprop. This is a figure from a paper, an Upland paper in 2016, which highlights why backprop is biologically implausible. And then there are different works that try to find more plausible training schemes. And on the left, we have the standard backprop. And as you know, as I've shown, it relies on global propagation of error signals through symmetric weights. And that is the backward pass uses the transpose of the weights involved in the forward pass to compute weight updates. So these symmetrical weights and the blocking of computation to propagate the error from top to bottom, these are not biologically plausible. And then on the right, we see different methods that try to get rid of these symmetrical weights. So for example, in feedback alignment, the author proposed to use a fixed random set of weights instead of the transpose. And then the network has to learn to use this signal to adapt its forward weights. And this works to some extent. It was shown to work. But again, as I said, these works were shown on fairly small data sets or even synthetic data sets, whereas with our approximate scheme, we have shown results at large scale. We think that sideways, for all these reasons, it is more biologically plausible. So just to mention a concurrent work, a theoretical work that is very similar in connectivity to ours, where they use diffusion equations to frame a backprop, and this actually results in a more biologically plausible training scheme. So yeah, they just gave a theoretical framework, and I am actually very curious to see if we can combine their theoretical findings with our empirical results to actually have a very principled training scheme. Okay, so to conclude. So I've presented different design principles for efficient training and inference by using either self-supervised tasks or by using pipelining in operations at both training and inference time. And the main idea is to exploit the temporal smoothness of videos to speed up both training and inference. And importantly, with our proposed schemes, the latency and throughput are not dependent anymore on the depth of the network. We can increase the depth now without affecting the latency. And the important next steps are to, as I mentioned, to define a principled theoretical framework for convergence with approximate gradients. And something that would be really interesting to see is to combine the skip sideways with self-supervision to obtain a local learning rule. So I would end with my vision to how to solve vision. So maybe some of you are familiar with LeCun's cake that I'm showing here on the right at the top. So basically, he's saying that the most important part in learning relies on self-supervised learning, because this kind of task can bring the most information in the learning process. And then the icing on the cake is just is the supervised learning, and then the cherry on top is the RL. So he's making these distinctions based on how much information you can get when you train your system. And I, from my perspective, my plan is somehow very similar to what he is proposing, but I'm just looking at it from the types of skills that the resulting models can get. So I think self-supervised learning is very important and should be like the very first, like the fundamental thing, the starting point, and that this can lead to a rough model of the visual observations, and then going to self-supervised multimodal learning will help us to ground across senses. So basically, to obtain common sense, obtain a model that is able to reason about its environment from the different senses that it has. So audio, vision, touch, maybe in the future we'll have language and so on. And then the very last thing, but still very important, is the part of active learning, interaction and intervention. So maybe this would be equivalent to the RL part that LeCun calls the cherry on the cake. I think this is actually more than just a cherry on top, because I think this is crucial for learning a causal perceptual model of the world. So I think that only by intervention, only by changing the state of the world, only then you can learn a causal, a fully grounded causal model of the world. So, yeah, and just to say, when I say intervention and active learning, I'm not really referring to this paper that is very often cited. Just so this was a study back in the 60s when some authors did an experiment on kittens, and they concluded that if kittens are not able to see their limbs moving, that they don't learn vision well. And it's been very cited, and it's used even today in many presentations. But just so you know, 10 years later or 15 years later, it was debunked by other researchers who showed that actually the environment was very boring for the kittens who couldn't move themselves. So because the environment was boring, they were not attracted to it. They were not drawn to. They were not paying attention to the environment. So that's why they didn't learn to see. So yeah, I thought that it's good for you to know. People don't cite the debunking experiment. They all cite the original experiment, but I think that's a wrong. The original experiment draw the wrong conclusion. But even though, even in this case, I still think that interaction is very useful for learning. So I guess my final note on this is that as a scientist, as a researcher, you have to question always. You have to question everything. Don't take things for granted. Try to understand things your own way. Don't take others' understanding for granted. Try to look at things in a different way, because then you might come up with original ideas on how to improve existing methods. Okay, and I think this applies in the everyday life as well, not only in science. Okay, thank you. If there are questions, I'm not sure if we are late. Okay, if there are some questions, as Razvan said, I'm also on Slack, so I can also answer questions there.
Maybe I will step in as well, and I can read the questions for you, Viorica.
Okay, I stopped presentation now.
Okay, so the first question was how to deal with relativity in motion. For example, a person moving as versus the person who is stationary.
So I'm not sure if this is referring to like using ego motion or using external view of the person. So I guess if it's ego motion, I think that gives us already a really crucial signal, because when you have a person moving, like if you have active vision, then you have control over the camera, and then you can predict the changes that you will observe in the visual field based on the actions that you're taking. Like if I rotate my head, I can predict that I will see now this lamp instead of this screen, and so on. So using active vision actually gives you extra learning signal. But then you also have like different degrees of freedom to control. And generally, I did some work in active vision using reinforcement learning, because then you frame the process as as a decision process where you can take discrete decision where to look and when to look in the to process your input data. And I think this is also, I didn't mention this line of work, but this is very important, like to decide which data to process, because if you have limited resources, which you do generally in a real-time system, in an embedded system, you cannot afford to process all the data that you have around you, and to process it at the highest resolution possible. So then you need to choose what is most useful to process, and that is active learning, which I think it's a really great direction. And I started working on this myself with the robotics team.
Excellent, thank you. The next question is, could you please give a definition of causality? I don't quite understand why 3D convolutions would be more tricky than 2D ones. In what way are we looking at the future? Is it complication of computation during backprop? Question.
So what I mean, yeah, probably this is an abuse of terms with causality, because it's used in different ways in different fields. So by causality, I mean a model that reasons about that computes is information from the data that it's seen, so that it doesn't look into the future to make decisions for the present, because the future is not available. You can make predictions about the future, but you cannot see the ground truth. So you cannot see the actual data in the future. And 3D convolutions, they have this symmetrical receptive field. So to compute one unit at time t, you have a 3D kernel, which has dimension k by k by k, and k, the first two k, let's say, are in space. So you have, like, let's say, a 5 by 5 filter, and then the last dimension is in time. And for that, you would look into the future. And these 3D convolutional models, they were designed for offline processing of videos, where you have access to the full sequence of the full video sequence. But that does not apply when you go in a real-time application where you receive frame by frame your data. You cannot use that kind of computation, right? Because at time t, you only have seen frames until time t. You cannot, you don't have access to t+1, t+2. And that's why I said that you can use masked 3D convolutions, which effectively just zero out the part of the kernel that would look into the future.
Mm-hmm. Thank you. Okay, now we're moving on to next question, which is, do you think vision can be solved by fully connectionist methods, or is it some form of symbol manipulation is necessary?
So I guess learning as opposed to symbolic methods. I do hope that learning will take us all the way. But what I think is important, and I didn't mention at all, is evolution. Because I think now we are putting a lot of pressure on one model to learn everything like starts from scratch, and to learn everything like end to end. That's what we call end to end, within one lifetime. You have one attempt to learn the right features. But in this, we're ignoring like evolutionary approaches, where we should have populations and then we should have different generations, where you have the chance to improve. Like, okay, you took one step, you learned some tasks, you did, you obtained some accuracy, but then you should be able to try different configurations in different generations to try to actually achieve a good like the best performance possible. So I do think learning. So yeah, for me, it's learning and evolution that should be combined to actually solve vision. And I think in a sense, so it's not at all the same with evolutions and populations, but the way we are reasoning now about pre-training in a self-supervised way and then going to fine-tuning on downstream tasks, this already brings this kind of idea of multiple layers in training, like on a temporal scale. But yeah, I think we need more also evolutionary approaches brought in.
Mm-hmm. Excellent, thank you. And one final question. And I remind everyone that we can take the questions to the Slack. So the final question would be, how would you deal with non-IAD data, since SGD does not work in that case? So I think that is meaning specifically to video, probably.
Right. So I think in Sideways, we are trying to exploit the fact that the data is correlated, and we are relying on that to like we are trying to exploit that, to exploit the redundancy and the correlation that we have in videos. So we are still computing gradients for a sequence, and we are averaging. So one sample for us is still one video sequence, and then we have different samples. We are still in the SGD kind of setting where we have different video sequences, like we train over a batch, and those are IID. But the way we compute the gradients for one sample, that is there that we are exploiting the correlation in the video. But across videos, those should be IID.